Hi, my name's Andrew McLaren, and I wanted to talk to you about Snell's law, which has mostly to do with refraction, but also is related to reflections. And today I'm going to go over an analogy that I find incredibly useful when I'm tutoring this. Usually, if I do this little car analogy, it really clicks for most students. But I'm also going to be going over the formula and a simulation, which will relate more to this reflection piece. And that should help you conceptually understand what's going on here with these various pieces. And then we'll do a couple example problems to help you see how this works with actual math. So before we do the analogy, let's just talk a little bit about this diagram where we've got the light going in, and then there's this other surface, usually it's like some water or glass, and the light gets bent going from air to the secondary medium. So that medium, its density is going to affect how much it bends. And people get a little bit confused with like, okay, if I'm going into the more dense medium, is it like, how is it turning? Is it turning towards the normal line or away from the normal line, and why? And there's this analogy that I like to do with a car going on a paved road and a dirt road, which will really help us understand this. I did want to also mention this is oftentimes in problems with like spear fishing, where you're trying to see where some object is, and it might appear like it's here to you when you're looking at it because your brain thinks the light's going in a straight line. But because the light's actually getting bent, the object may be in a different place than where you actually think it is. And so there's an example right here of someone in a pool where the light has been refracted with the water. So it looks like their head is different place than their body. This person really is here, but they appear to be over there due to this refraction. So I have this analogy where you can imagine they're in some car. I know it looks like just some four-wheeled box. I'm not the best artist, but this analogy is really good because basically you can imagine this car on a paved road, and maybe there's some dirt road or sidewalk or side of the road that's not paved. And this car is going on the paved road. It has some friction, but not very much. Then when it hits this barrier between the two, the wheels that are on the side that hit it first will get slowed first, and so it gets turned towards this the normal line where there's more friction, which is analogous to water or glass being more dense than air. And so when this light comes in, you can imagine usually they'll say there's like a bunch of little light waves coming in like a packet kind of like this. You can imagine all these light waves coming in. The ones that hit this surface first will get slowed first. And so the wall of light gets turned a little bit. So you can imagine this as those wheels getting slowed down first before these wheels over on here. And with that analogy, you can imagine this car turning. And this works for going both ways. So if you're going from the medium that's more dense to the one that's less dense, it's kind of like the dirt road here. And it will have these wheels that hit the paved road. They're going to have less friction in this analogy. So those wheels will get to go faster. So because they're going a little bit faster, you'll see some acceleration with the car. It actually turns a little bit. And you can imagine now that this is going to be turned this way, so it's got a bigger angle relative to this normal line when we're in this less dense medium, or the thing with like less friction in this analogy. So you can imagine that's kind of like what we have here. This has a different angle, so you can see it being turned a little bit better. So the less dense one will have a bigger angle is the main idea. And you can think about that car analogy, and that really helps me. There's also this one formula, which we talked about on the last page. Let me just go snip that. All right, so we've got this formula with N1 and N2. So those are the densities of the material. So you could imagine where we have a situation where N1 is bigger than N2, meaning this is more dense. And so if N1 is bigger than N2, the sine angle here should actually be a smaller angle. So this will be smaller, and this will be bigger in terms of its actual value. So if you were to look at the sine of that angle, these will be bigger when we see the this like N1 being more dense, then N2's angle should be bigger. So if we're thinking back to our image here where we were talking about this, it's like, okay, The thing that has a bigger n value has a smaller angle. And that should give us that relationship in the formula here. There's other ways to write this formula. I like this because it helps you see like, oh, in this case, the top of the fraction is bigger than the bottom of the fraction, and that corresponds when we have the thing with a bigger n value having a smaller angle. So this is a simulation from PhET, the bending light simulation. It's pretty amazing. I really like this. I used this with my middle school students when we were going over the standard around how light is reflected or refracted through various materials. I did not have them do the calculation with the math, but I did have them conceptually see like how these angles changes with the density. And the really neat thing about this simulation is also it shows you the reflected light and how you can actually get more of the light being reflected when this angle is really steep and less of it's being reflected when it's like more direct. If you've ever looked at a window and it's like maybe there's different amounts of light between the two sides, you'll see more reflection when you're looking at like this like sharp angle relative to the surface or like a big angle relative to the normal. So that's conceptually one way to think about this and to see this relationship. And then you can also imagine this being like that car analogy and seeing how this is going to get turned a little bit. So if we've got a like much more dense thing, so if we make this like really dense here, then that should, yeah, change this angle a little bit. So the more dense something is, the more it's going to turn, or the difference in density is going to cause it to turn more. So you can see if we make this really, really dense and not so dense, the one that's more dense has a small angle here. So that's how I like to think about this. You can also do some pretty cool things with this simulation where you can add different shapes and you can actually get the light to refract in a like a totally contained shape, and it's a pretty cool tool. You can have this like hit this circle just right, and if you get it just right, you can actually separate the light into different angles. It's kind of interesting. I think that you saw it for just a sec. Yeah, there was like, you can get this thing to be like internally reflected. And my middle school students loved playing around with this, getting that angle to keep the light inside the shape. You can build all kinds of weird little things using this tool. I would highly encourage you for checking out light and how it moves as a wall. Thinking about kind of like that car helps me a whole lot. One other thing I want to point out, this is going to be relevant for some of our problems, is that you can have there be an angle where none of the light now is able to be reflected or refracted, but that only happens when you're going from something that's more dense to something that's less dense. If I have this be more dense, like any angle coming in will give some angle going out. But if I can make this be less dense, suddenly this light can all be all reflected and not refracted at all. So there's this point at which this gets turned so much that the refracted light is going straight along the surface here. So you can see that this approaches going at a 90-degree angle relative to the normal here. So this is going to be like 90 degrees for one side and give you some other angle for the other side. And that should hold to the same relationship where we've got the ratio between those two n values for the density of the material. So you can see that at some point, all of the light is going to be reflected, and that's when none can be refracted. So none is actually going into this lighter medium. It just all ends up getting bounced back. So for these example problems, I'm going to go in depth with this first one where it's just like step by step, what do I do? And then I'm going to go over the already worked out problems that I have here, talking about that case where all the light is being reflected, none is being refracted. So those problems will be a little bit quicker, but they're conceptually a little bit more complicated. So if we look at the sample one problem, basically we have some light that's going to be going from air to this fiber optic. And there's a difference in density here where we've got the air is going to be, maybe that's N1 or NA if you want to do NA and NF. So N1 for air it looks like this is just a value of 1. The default is 1, so when we have air, it's just got this 1. But for the fiber, for that, that looks like that has a value of 1.44. So this is more dense, and it looks like there's some light that's going to be bending. We do have the normal line right here. So this is what we call the normal, which is 90 degrees relative from the plane or between the two mediums. So you've got like medium air and the medium fiber. This is that normal line. So if this angle of incidence is 22 degrees, then that means that it's 22 degrees from here. So I'm just doing like a little estimation like that. And we can imagine the car coming in, it's going from something with less density to more density. So it's hitting something and it's getting slowed down a little bit. So I'm thinking that this is going to be turned a little bit so this angle is even smaller. So this was 22 degrees. And I can see that this should be smaller. So I kind of conceptually know that I should be getting a smaller value here. And then if we think back to our formula, we had that n1 over n2 is equal to sine 2, and then sine theta 1. So we can start kind of plugging in these numbers and conceptually thinking about what's going on here. We can think of the air being that 1, so we've got the 1.0 on top and the 1.44 on bottom. And then we've got our angle 22 degrees. That was for 1. So we've got sine of 22 degrees. And then we're also solving for this unknown angle right here. So this is that sine theta 2. So if we take this information, we can then substitute. What I would do for this is substitute in for the sine, that sine 22. So if we get our calculator here, and we take 22 degrees and we sine that, and then we get a 0.3746. That should be a good enough estimate for us to work with. Just put an extra sig fig and it should be okay relative to that n. Physics sig figs are a little bit more loose than what you may be used to. So we've got that 1.0 and 1.44. So I know whatever I'm gonna get here, this sine value should be less than 0.3746. Conceptually, I should be able to check that as well. So if we just do a little math, there's a rearrangement here where we can do sine 2 is equal to that 1.00 over 1.44, and then times that by 0.3746, and we'll see what we get there. So if we take this number, times that by 1, divide that by 1.44, we get, yeah, what is that, 0.2601. So we can then say, like, what is sine theta 2? So if we take 0.2601 and we do the inverse of our trig function, so we need to do inverse of sine, then we get 15, an angle of 15 degrees. So we can say sine theta 2 is about 15 degrees relative to that normal, or that first green line that I drew in. So we are able to see that this smaller value right here was 15 degrees, which conceptually makes sense. The more dense thing should have the smaller angle. So that's how I would go through one of these problems. And you can, even if you wanted to, you could, I think it might end up messing this up a little bit, but you could end up doing this exact problem with the simulation where you have 1 and 1.44, I think was the angle, and then you could even get this down to like the 20-ish degrees or 22 degrees. So I think that would be around there. And you can see like, oh yeah, that's close. I mean, I'm not getting it exactly right, but it's pretty close. So yeah, that's how you would do these problems. Okay, so this problem is a little bit more challenging than what I've seen in high school, but it's very typical in a college class. You'll have these problems where they give you these angles, and so from those angles, you basically can summarize the relationship between N2 and N1. You can say like, okay, N2 is this much more dense than N1 if you're able to plug in their sign values. So that's basically what we did in this problem. And then conceptually, what you can think about is that this is some angle where all the light's being reflected. If you had a smaller angle, some would be refracted, but there's this like cutoff point where this is actually at like 90 degrees, and so there's some angle that you can get which corresponds to 90 degrees. That's the cutoff point. So if you go to a bigger angle than that, all the light is reflected. If it's smaller, then some will be refracted still. So there's this little cutoff point at like sine 90. So if you can just plug in sine 90 into this relationship, um, basically then you can say like, okay, I had this sine 1 over sine 2, which is also equal to this other sine 1 over sine 2, but like in initial and final. So there's like some two angles here. You can think of this as our initial. And then we're going to have, there's this other situation where it's like, okay, well, we have the same relationship between N2 and N1. So these angles should have the same ratio between the two. And so we were able to isolate for that and say like, okay, well, what would X be? Okay, well, that would be the value of the sine. And so if we then do the reverse sine function, then you can see that that would be 50.4 degrees, which should conceptually make sense. If we're thinking about this, there's a smaller angle for the one that is more dense and a bigger angle for the one that's less dense, which corresponds to what we were saying earlier. Like this is 50 degrees compared to 90, whereas we were having 36 degrees compared to 50. So you can see that like the smaller numbers on top still in this situation. And so it's the same sort of relationship. There's another problem here that I have. It's the same sort of setup where they've got the N values for the red and the blue light, and they've given you the relationship of N2 over N1. And so you can assume like, okay, well, I now know that sine 90 is one of these, and the other one has to be some value. Now, if you accidentally flip these, the problem isn't going to be doable. Like if you accidentally had sine 90 on top, because then the other value just doesn't work, because instead of having a very big number, you got now a very small number if you're thinking about the ratio that way. So here the x should have been smaller than 90. If you had accidentally put x down below and sine 90, then x would have to be a bigger value, which just doesn't make sense conceptually. So that's one way to think through these Snell problems that are a little more challenging. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there. And we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.